Howdy everyone, my name is Hao Huang, a PhD student from Texas A&M University. Today I'm going to present the paper, Real-Time Power System Simulation with Hardware Devices through DNP3 in Cyber-Physical Testbed. In this presentation, I will go through the following parts: the background of cyber-physical power systems, a brief introduction of DNP3 protocol, the proposed hardware in the loop testbed using DNP3, the configuration and the validation of DNP3 communication between the hardware and the software. There is an exemplar of data acquisition and the control in the proposed testbed. As we know, modern power systems are made of power equipment, including the generators, transformers, transmission lines, etc. And there is also cyber network, which consists of communication devices and the management software. In between the cyber and the physical layers, there are sensors, IEDs, and ICS protocols that enable the data can be collected from the field physical devices to control center. And operators in the control center can issue different types of command to physical devices. The Distributed Network Protocol 3, which is DNP3, is commonly used in power systems for data acquisition and control. It is a protocol for transmission of data from one point to the other through serial or Ethernet communications. It provides the rule for remotely located computers and the massive station computers to communicate with each other. The figure on the right side shows the DNP3 communication between a master and an outstation. Once the master sends a request, then the outstation will respond by supplying the data or executing the command. In this paper, we propose an idea to use DNP3 protocol to build a hardware in the loop testbed, where we use the Power Dynamics Studio runs the real-time power system simulation and use the Schneider's real-time automation controller to be the DNP3 master. The Power DS has a functionality of DNP3 to make the software as a standalone DNP3 server and generate a DNP3 package with the real-time power system simulation data. And the RTEC is a standard industrial controller device which has been used in substation and control center for data acquisition and control. As shown in this diagram, the RTEC or the DNP3 master collects the analog and the binary data from the real-time power system simulation, and it can also issue the control for both analog and the binary to the devices in the DNP3 outstations in PowerDS. In this presentation, I will go through the detailed configuration of both software and hardware to establish the DNP3 communication for data acquisition and control. On the PowerDS side, we can create as many as outstations. And for each outstation, we can insert different type of DNP3 data, like the binary input, binary output, analog input, and analog output. And we can choose the corresponding field, such as whether we want to have the status or whether we want to have the measurement. And there's also event class to be selected. The event class determines how frequent the data will be pulled by the master. And here's an example of outstation with all the points in it. For the RTEC side, it is configured through the software SCL accelerator, where we have DNP3 data under different sections. And for each section, we can add as many as tags for the data that we want to collect it, and we want to collect. And we can also change the tag name to give the users or to give the operators a better understanding of what the data he or she will be expected. Like for this example, we give the substation information, the device information, and the data type information. To have a correct data transition and understand what we are expecting, we are doing a one-to-one map between the DNP3 outstation to the DNP3 master, which is based on the point number or index for the DNP3 data under each catalog. Here is an example of the analog input data that's mapping from the outstation to the master based on the numbers I mentioned. And once we finish the physical information configuration, we are moving to the cyber information configuration, which is the communication parameters. Since in this paper, we directly connect the RTAG to the power DS. So to have a valid DNP3 communication, we need to make sure both devices are under the same subnetwork. The power DS is running in a Windows machine, so it shares all the network information for that computer, and it can have multiple IP address. But the RTAG will have fixed IP address, which in this case is the 172.168.2.2. So we need to find the IP address for the DS under the same subnetwork, which is the 172.168.2.10. And then the IP port is where the DNP3 communication will run. And for both sides, it is 20,000. It's a standard settings. And one more thing I want to mention is there is a server DNP address information we need to fill. Since both RTAG and the DS can have multiple DNP3 outstations and clients, so with the one-to-one mapping, each master will have one corresponding outstation. So the server DNP address will be that outstation number. Once the DS and RTAG are being configured and we set them both online, we can check the DNP3 communication through their logs. On the DS side, there is a summary of how many clients has been connected and what are the incoming and outgoing DNP3 messages. On the RTAG side, there is a section called controller, where we can see there's a lot of tags over there. The highlight part are the one that can be used to monitor the communication between the outstation and the master. The offline tag should be false when the communication is established, and the message sent and the received counts should increase simultaneously. And there are other tags which can also be used to indicate the communication. In this presentation, I'm going to give a more detailed presentation, a more detailed exemplar of data acquisition and control. We use the substation from the synthetic 2000 bus case, where we have 2 generators and 7 branches. So for the analog data, analog input data, we create 18 data points for all those devices, real power and reactive power information. And for the analog output part, we only configure the generator set point data to control the real power output for the generators. For the binary input part, we collecting all the binary status of the devices, as I mentioned. And the binary output is the same, but the binary output is used for master or clients to control the corresponding devices. In the RTAC, we also have the corresponding analog input, analog output, binary input, and the binary output. All the data is mapped based on the point number. So once the software and the hardware are online, we can see the data that's being collected in the RTAC through the tag section. I expand the tag for the branch 5047 to 5260, the reactive power, which is the same one as the information showed in PowerDS. And here is another example of the binary status of that branch. And we also have the corresponding data. And besides the data, we can also check the validity of the data to double check the communication status. And here's an example of the control implementation from the master to the outstation. For here, I expand the binary output tag of the branch, and we can see there are several actions could be done, including the pause, latch on, latch off, trip and close. And for here, like I sent a trip command by setting the value as true. And here is another example of control the generator output. And I set the generator real power output as 1000 here. And in the DS side, we can check the log of the event, and we can see there's a line being open, and the generator has been changed to 1000 megawatt real power output. To wrap up, this paper presents a cyber-physical testbed implementation using the DNP3 protocol to bridge between the real-time power system simulation and industrial hardware devices. It can help us to mimic interactive control and response in the field. For future work, we can incorporate real or emulated communication network between the software and hardware to have a more complicated view of the cyber-physical power systems, where we can perform different adversaries, and we can also develop the defense mechanism. The authors would appreciate the support from the US Department of Energy and the National Science Foundation. Thank you.